All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you are all doing okay today. We are like T-3 classes. We were right there. We're right at the end. We're going to keep talking about virtual memory today. My goal is to talk about allocation policies, as you may or may not see in front of you right now. And then if there is time at the end of today's lecture, we're going to move on to talking about paging. But before that, I want to spend some time talking about the assignment again. At the end of last class, we were just like, I'm finished describing the assignment. No time for questions. No questions, please. Let's have some time for questions today. And there have been some really good questions on the forum that you should check out if you haven't checked them out already. I also want to spend some time talking about the final exam, the format of the final exam, what you should expect on the final exam. And then I want to talk a little bit about some of the learning outcomes in the course to give you a sense of where you are, where you've been assessed, what you've been assessed on, how you've been assessed, and then what you may expect to be assessed on in the final exam. So by the end of today's lecture, the main thing that I want you to be able to do is compare and contrast free space management or allocation policies. So I want you to be able to apply allocation policies or free space management policies, and then I want you to be able to compare those free space management policies in terms of how they perform on different workloads. That's the only learning outcome we have set for today. If we get to paging, great, we'll talk about paging, but this is the main thing that I want to accomplish today. For assignment 3, there's one tip that I'm reminded about every time I've done this, and then I always forget to tell people because it just kind of just sits in my head and I don't ever write it down. When you're doing the listing of directory content, when you're doing like getting files out of the file system, using a recursive approach is a great idea. Using a recursive approach is a great idea. It's a tree structure, so use recursion to go through the process of building up that tree. You're moving around in a file, though, with seek, lseek. You're moving around in a file. And when you seek in a file, the state of the file is not kept in your call stack. It's kept in the open file table. So as you're making changes with lseek, so you recurse on a directory entry and you seek to a new cluster, that's not going to go back to where it was before when you pop off the stack. So my advice to you for this is keep track of where you are on the cluster heap just before you do the recursive call. Yeah?
This is maybe too technical, but maybe...
No, please go ahead.
Seek cur with like offset 0 would return the current position.
Seek cur with an offset of 0 returns the current position. Are you telling me that or are you asking? Let's take a look. Let's look in the manual page for lseek and seek cur. lseek in general returns the amount that you've read. And if you're keeping track of the amount that you've read and which cluster you're in when you were called, you know approximately where you should be as you're stepping through it. But I'm not sure that calling seek, lseek with 0 returns. Yeah, because it's just going to tell you how much it has seeked.
Pretty sure it returns the offset from the beginning of the file, though, isn't it?
Offset.
Like for the return value of lseek.
Return data. That's not really what we're looking for. We'll always return the offset. No, this is also not what we're looking for. Return offset. Return value. Upon successful completion, lseek returns the resulting offset location as measured in bytes from the beginning of the file. All right, there you go. So that'll tell you the last place that you were. And if you lseek 0 seek cur, you're moving nowhere, but you're getting where you are right now. Yeah.
So it's a valid.
That seems like a perfectly cromulent approach to me. Yeah, it seems like a good approach. Seek 0 bytes, find out where you are right now. Thanks for the tip. What's that? Trust issues. I will vouch. I will vouch for this voice. I will vouch for this voice. If you can throw me under the bus. Okay. So that's a little bit of a tip. Just keep in mind that lseek has side effects that are not on your call stack. They're tracked in the open file table. And then just time for questions. So yeah, yes. Sure. The volume serial number is in the boot sector. And I'm looking for table 3 or 4 here. So that's this volume serial number. I'm kind of just gonna straight up say that whatever you print out is the right value. And I'm gonna say that because you're using my struct that contains this property, and you will just have read directly into my struct. So whatever you get out of that is going to be the valid value for the volume serial number. It's going to be a number that is 4 bytes in size, so it's going to be some 32-bit number. It's a number. Yeah, it's a number. I mean, you could print it out as a hex value, and then it'll have letters in it if you want. But yeah, it's a number. Yeah, yeah. So whatever you get is yeah. Yeah.
And the number of allocation formats mentioned
You can assume that there's one allocation bitmap, yes. In the same way that you can assume that there's one FAT. You can't assume that the allocation bitmap fits on one cluster. So you do have to build up a cluster chain possibly for your allocation bitmaps, especially the 1 sector per cluster volume. But there is for sure just one allocation bitmap. Yeah. Do you have to use open and close and read and lseek and stuff? No, you don't have to. They're not forcing you to. Just in the context of this course, I haven't talked at all about fread and fopen and using file pointer from the standard library in any way. So I don't really have a problem with that. Does it make your life easier? What's that?
It feels less archaic.
It feels less archaic because you have an uppercase file pointer instead instead of an integer. Hey, this isn't archaic. This is used in modern operating systems. Yeah. No, that's fine. I don't really have any reason to say no to that. Any other questions about the assignment? So Kyle's still running office hours. If you want to go meet with him, yeah. Uh-huh.
Last Thursday,
Some other guy. Okay. 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 There's one lab section that's in a different room. But there's one that's in a different room. There's one of the 4 labs. Okay. This is the first time I've heard of Kyle not being there, and I kind of trust Kyle, so I believe that he was there. What's that? Okay. Kyle's always there. You make it sound like he's actually just always there. Now we're arguing about what day of the week it is. Are there any other questions about the assignment? Generally okay with it? Yeah.
For like the stream extension, like the no fat chain, like that would mean there's, this is kind of a redundant question, that means there's like no,
Yeah.
there isn't any like,
So
we don't need to check the, like the bats.
yeah, so I'm gonna pop this up because I just want to make sure that everybody can see and hear what you're talking about. One of the properties in the stream extension directory entry, and then we have to go back to the general secondary flags to section 6.4.2, is this no fat chain bit that's in this general secondary flags field. When that bit is set, what it means is that you can read the stream extension and you can then immediately go to the cluster for that file and just read that many bytes because all of the clusters are contiguous. They're all right next to each other. And if you try to build a fat chain, it may not actually give you all the bytes. There might not even be one in the fat. What this says is just read the file. Just read the file. And this is typical for big files that are not fragmented across multiple clusters. Yeah.
If I read that many bytes, like, that would be data length?
The data length, yeah. So if we go back to the cluster chain, or the stream extension here, the data length tells us how many bytes are in the file. When there's no fat chain, when that bit is set, just read that many bytes from the start of that cluster heap. Location.
So it's really a big matter, like how many sector we know per sector, per cluster. If we already have it in the main root sector, like why do you have to name the name of the file like that? So we have to take into account, or because we already have that kind of information in the main root sector already.
Can you repeat your question, please?
Yeah, so we have, I just don't understand why you have the name of your file, like 4 sector per cluster, 8 sector per cluster.
The names of the files?
The testing input,
Yeah.
why you have the name like that?
Why do I have to name it like that? I'm really misunderstanding your question, I think. So,
But that kind of information we already have in the main root.
oh, why have I named these folders that way? I've named the folders that way because each of these different images has that many sectors per cluster. You could do that. I could have named the files just differently, volume 1, volume 2, volume 3, but I'm just trying to make it clear which volume has which properties before you even start reading in the main boot sector.
And how many, like, does it matter how many directory entry they have in one sector?
In one cluster. So each of them is going to have a different number of directory entries allowed per cluster. And that's going to be basically every directory entry is 32 bytes in size and your cluster changes. So for the 1 sector per cluster image, you can have 512 bytes in total per cluster. So 512 divided by 32 is 16. Thank you. Thank you. Thank you. Is 16 directory entries per cluster. With the 4 sectors per cluster, it's going to be 4 times as many. So 84 directory entries? No.
How does that depend on the sector instead of the cluster?
So because the cluster size is derived from how many sectors there are per cluster. That's just the way that we calculate how big a cluster is how many sectors are in it. So you have to know how many sectors are in a cluster to decide how many directory entries there can be in one single cluster.
I just feel that's maybe a big factor of the segment, that's why we need to define it that way. So it's not like if you the sector, then what sector just a that you need to know to calculate how big the cluster is.
Yeah, and you can get that from the MBR, and you should get it from the MBR. You shouldn't just assume that I'm going to put the folders in this naming structure. You have to read that from the main boot sector, but I've just tried to organize it this way so that it's clear which one is which. Yeah. All right. You don't have to file system check these images.
Inside a cluster, if we reach like a end of directory, there's never going to be any content after that, right?
No. So
Inside that cluster.
as soon as you've reached the end of directory marker, there's no more directory entries. Yeah.
How does the file system keep track of like which the cells are being used in which one?
It explicitly doesn't. So if you read the documentation, which I'm going to pop back up here again, and I'm going to go back up to the top of this page. If you take a look at the documentation for the fat itself, does it say it here? I don't know if it says it here or if it says it in the allocation bitmap part, but it very explicitly says that the fat itself is not used to keep track of which things are allocated and which are not allocated. It's the allocation bitmap that's used to keep track of which are allocated and which are not allocated.
Right.
And the entries that are into the fat, so the things that get you into the fat, are all from other things, the main boot sector or other directory
Oh, okay.
entries.
So if we were inserting, we'd have to check which of these, we'd have to check the bitmap and then,
Yeah.
okay.
Yeah, you have to check if you were to add write support to this, you'd have to check the allocation bitmap to find out which clusters are free.
Right,
And then once you know which clusters are free, then you can start updating the fat.
right. Okay.
Yeah, yeah. Do you have another question? Okay. No, you don't have to write anything. The only thing you're doing is reading. Yeah. So in the file, there's this file attributes. In the file directory, there's a file attributes property, and this is where you're determining whether or not this thing is a directory or not. I never remember. I think one means that it's a directory, but it's really trivial to find out because once you're starting to read directory entries, you know what the file name is based on the directory entries that come after that, and you can look at the output from the tree.txt file to see, like, is this a file or is it a directory? And then that'll quickly tell you which one it is. So don't take that I've said that this is one to be a universal truth. I'm pretty sure that's correct, but you can figure it out very quickly. That's the only thing that you really care about here is that bit, yeah. Yeah.
In sector-sized files, like it has like 3 files in it, but like 2 of them don't have extensions. Those are still files, right?
They're still files, yeah. They've got a bunch of garbage in them. One of them I made with the rand, so it's just random data, but they're actual files, yeah. Yeah. Okay. Okay. Good, great. Okay. I'm going to switch over back to the slides here. I hope that this is going okay. I hope it's going generally okay. But let's switch to talking about the final exam. We've got 1 week before the final exam happens. It's less than a week technically because it starts at 9 on Tuesday morning. The content for the final exam is cumulative. It is a comprehensive final exam. So the content that can be on the final exam is everything from the course. It's all the course material from the beginning. However, you've been assessed a lot on stuff from the beginning of the course already, and I'm going to talk about this in just a second. You should kind of make some educated decisions about what may or may not be on the final exam, and I'll show you what you can use to make those decisions in just a second. But everything from the beginning of the course is eligible to be on the exam. And the time that I'm going to do that is right now. So let's go back to lectures, week 6, lecture 20. I've posted this file on the course webpage, so you can find this under today's lecture section. I went through the process. In me starting to prepare the final exam, I've gone through the process and I've just taken all of the learning outcomes out of the schedule and I've put them in here week by week and to organize them. And I've tried to take the outcomes that I've already stricken and just they're not in there anymore. And I've tried to remove the duplicated learning outcomes. So the virtual memory ones, there's like the same learning outcome 3 times, beginning, continuing, continuing. I've just put it once here. These are the learning outcomes that are in the course. and these are how you have already been assessed on many of these learning outcomes. So for example, for processes there, write code that uses system calls to create and manage a process. You did that on assignment 1, you did that on lab 1, you did that on the term test. Given that you've done that on 3 different things, I am almost certainly not going to ask you a question about writing code to manage processes on the final exam. I will almost certainly not ask you questions like that. Things that have been assessed on a term test already, probably not going to ask you the same question. Like, I'm not just going to go back and copy paste. I may ask you questions about the same thing, but still it's kind of unlikely that I'm going to ask you questions that I've already asked you on a term test. There are some things going back to the beginning of the course that you have not been assessed on at all. So for example, compare and contrast the shared memory and message passing programming models as their relationship is seen through the lens of synchronization. You haven't done that in anything in a way that you are being assessed on that learning outcome. We talked a lot about it when we were talking about read and write and that block keyword and then the comparison between pthread mutex lock and that sort of thing, but you haven't answered that question anywhere. Going forward through the course, you can see that most of the first half of the term has been covered in a variety of different places. And then we get to the second half of the course, starting in week 3 here, where you haven't been assessed on really any of these learning outcomes yet. Assignment 3 is limited mostly to the writing code to read a file system. And I've kind of marked this as you have to be able to do this to be able to do the assignment. Like you have to be able to go through the process of drawing this relationship between clusters and sectors and that sort of thing. You have not been assessed on a bunch of these things. So the IO scheduling, physical representation, file system implementation, you've been assessed on write code to do it, but show how, explain how, none of this stuff has been assessed yet. Choosing a RAID level, this was that exercise we were doing in class. Here's an example problem, which RAID level should this person pick? And then the virtual memory stuff that we're talking about right now. So none of the stuff you've been assessed on. I've started building the final exam. I haven't finished making the final exam yet. I am kind of thinking though that I'm gonna just delete that week. I'm just gonna delete that part. In terms of what, I'm going to make sure that you all saw what I just did. This part here, this is the second half of week 3. I'm just going to delete this. I'm not going to delete it from the document that's up there. I'm just going to delete it here. And this is what I'm using to assess, to build my final exam. Again, that was what was there before. Part 2, IO scheduling and physical representation, and now it's not there anymore. So I'm not going to I guarantee you that there will be no questions about that part on the final exam. Yeah, please. I will not update this file. I will not update this file after class, no. You are here right now, you saw me do it. The people that are on the stream, hello, you saw me do it. The people that are watching this after class saw me do it, but I'm not gonna update the file. Because I actually wrote all this in Markdown and I just put it into this document for making it easier to read in class. So this is not like my source document. Okay, so like I said, the things that you've been assessed on multiple times are unlikely to be on the final exam. The things that you've been assessed on maybe once, that might be reasonable to show up on the final exam. The things that you have not been assessed on at all, those will almost certainly show up on the final exam. Those will almost certainly show up on the final exam. The test will not have C programming in the same way that the term test did not have C programming. I'm not going to expect you to write any C programs. I'm not giving you manual pages, so I'm not expecting you to write any C programs. As of right now, I'm not expecting you to write any programs, but as I said, I haven't finished making the test yet. But we also really haven't done a lot of coding stuff in class in the second half of the course to give you some sense of what you might be seeing on the final exam. You may be expected to read C or C-like code in the same way that you were for the term test. I might give you some code and ask you some questions about it, but I'm not going to expect you to write anything that's in C. Seating is going to be assigned in the same way that it was in the term test. I'm going to send you this email on Monday before the test, and I'm going to guarantee that it will be out of my outbox by 12 p.m. I don't know when you will receive it, but you should receive it very soon after that. Same with the term test, though. I'll bring my stuff, so I'll have the spreadsheet of where people are supposed to sit if you didn't get the email. But if you don't get it by like 2:30 on Monday, send me an email and let me know, and I'll try to get back to you. There's still no room assignment. I emailed the registrar's office to ask, like, hey, where's this exam going to be? And they didn't email me back before I left my office, so I don't know. I'm sure they'll let me know eventually. Worst case scenario, I will send all of you an email and tell you to come here. Worst case scenario. In terms of the format of the final exam, you can expect similar kinds of questions where I'm asking you to like apply concepts that we've been talking about in class. There's going to be very little like define these terms for me, please, and a lot more apply the things that we've been doing in class to the same kinds of situations, but slightly different. There may be some multiple choice questions on this exam. They're not going to be the majority of the exam. Like if there's 10 questions, maybe 1 or 2 of them might be multiple choice, but they're not going to be the majority of questions. In terms of the length of the exam, you may have noticed that the term test was a little long. It was a little bit long. That was not intentional. I wasn't planning for that to happen, but when everybody's still here and there's like 5 minutes to go, that's a little bit of a long test. So the length of this final exam isn't going to be like twice as long as the term test. It might be like 1.2 times as long as the term test, maybe something like that for a 2-hour final exam compared to a 75-minute term test. Are there any questions about the final? Locking questions? There's not going to be any questions about p-thread locking. I don't have any questions. I'm going to rephrase that. I don't yet have any questions about p-thread locking. I have a question that I've written already that is related to the concept of locking, but it's not about p-thread locking. Yeah. That was just not quite a hand up. Never mind. I've written 8 questions right now, but and then there'll be like subparts to those questions, but I'm not done writing the exam yet. As a student, what would I do? I'd panic because I have an exam in a week. Like my advice would be that we've done certain activities in class. We've done certain activities in class. I pointed at specific outcomes today to say, hey, we did this activity in class for at least one of them. Yeah, so maybe be able to do that. The textbook informs you a lot about how to do those activities. I know it's a lot if you've fallen behind. Believe me, I know it's a lot. I read the textbook. It's a lot, I know. But in terms of like what I'm going to ask you to do, it's probably more about applying those ideas than just rewriting the textbook to me in an answer. If that makes sense? Yeah. Okay. Well, you allocate your time as you want. Yeah. Yeah. I don't have a hard number that I can give you, no. But again, the majority of it is going to be on stuff that you have not been assessed on already. That's what's the focus of the final exam is going to be on. Any other? Yeah. Yeah. It's empty. Well, that was, can you download it and open it in Word? If it does the same thing, that I didn't mean to do that. Haha, joke's on you guys. No, that's not at all what I meant. It's a PDF that's named docx. Okay, that's great. Thank you, Learn, for that. Does it work? Does it actually render correctly? It's the same thing.
Yeah. See you next time. Yeah. It says no.
Brute force that password. PDF document. Okay, here's what I'm going to do. I'm going to delete this file. And then I'll never upload it again. That was a long time ago. This is the wrong course entirely. What is going on here? Why are there 13 weeks? It's because it's Comp 2150. And it is before final.docx. It is a 13 kilobyte file.
Are you gonna remember to delete those things from the actual source file?
I might have just saved it before I uploaded it. Let's see. What did I remember to do this time?
Oh, is this that document?
Yeah. Oh, yeah. Thank you, Learn.
Yeah.
All right, okay. And would you look at that? The part that I said I was going to delete and never upload, it's deleted, it's gone, and it's uploaded. Okay. We're good. Yeah, yeah. That's a completely fair question. If I ask you questions about exFAT, would I expect you to have memorized parts? So for example, something like this, the file attributes field, would I have expected you to memorize that? No. No, I would never expect you to memorize this because it's a table on the internet that you can just go and look at. That doesn't tell me much about whether you understand how the file system is structured. The kinds of questions that if you were to be asked about them on a final exam about something like exFAT is like, tell me about how to go through the process of getting a file out of it. Not write code, but like, tell me what you would be doing. Here's a FAT, build a cluster chain. What kinds of structures might be updated when we're making changes to the file system, which is one of the learning outcomes that you've got. Like those are the kinds of things that I'd be asking you to do. If I really did want you to tell me about directory entries and stuff, I would republish this table for you in the exam. If there was really like minute information about it, I'm looking for you to be able to demonstrate that you have a high level understanding of the structures of the file system and not the tiny details of like how many bits are in this field. Yeah. Yeah, it's the same thing. So I'm not going to ask you like how many bytes are an inode, because if I wanted to know that, I would tell you one for one. And then if you wanted to know in the real world, you could just go look it up. Yeah, yeah. I don't know where you heard that. Oh, well, VSFS is like, it's not a real file system. It's a file system that is part of a learning operating system. And EXFAT is a real live actual file system. Like it's on USB drives, it's on all sorts of stuff. Yes. Maybe both. Are there any other questions about the final exam?
So aside from the VSFS and XFAT, the other ones,
Like the list of file systems?
yeah.
I'm not going to ask you about the list of file systems. Yeah. That, like, so I forget exactly what I said during that class, but that list of file systems is more just like, hey, look at this wide world of file systems, and that's the end of that conversation. It's not meant for you to tell me in detail about how ZFS works, or why you would choose ZFS over something like VSFS. It's an obvious choice. You choose ZFS, but it's kind of irrelevant to the course as to why you would choose that. It's obvious to me that that's the choice. Okay, we have beaten the exam and the assignment to death, so let's try taking a look at some other stuff. Okay, so our topic, our main learning outcome for today is to be able to compare and contrast different free space management policies. And the motivation here is directly related to virtual memory. It's directly related to the virtual memory stuff that we've been talking about. Base and bounds is the first approach to doing virtual memory historically in what we've talked about in this class. And the idea with base and bounds is that you take physical memory. You've got 64 kilobytes of physical memory. You have 24 gigabytes of physical memory. You've got whatever. And you logically separate that. You break it apart into fixed size chunks, fixed size blocks. And then within those fixed size blocks, you allocate entire address spaces for processes. The base and bounds part of this is, where does the virtual address space for this process start in physical memory, and how big is it? And we can keep those two registers or two values in our process control block for every process. We're logically separating physical memory, and we're allocating the entire address space with base and bounds. The way that we manage free space in this is really straightforward. And in fact, it's really close to what we're doing with our file systems. That block is either allocated, there's a process that has a virtual address space there, or there isn't, and it's free for use. You can put a new process into that one. You could use something like a bitmap, an allocation structure, to represent free space for this approach for virtual memory. Which blocks are used, which are not used. When you want to launch a new process, so you need to allocate some physical memory for a virtual address space, simple. Just find the next free block. They're all the same size. You're allocating the whole address space. Find one that's free and dump it in there. There are no free blocks. Crash. You can't actually create a new process because you cannot allocate its full address space. Segmentation came after base and bounds in the form of, we've allocated all this space and we have a bunch of stuff in the middle that has been allocated, but we're never actually using it. We have internal fragmentation with base and bounds. That giant space between the heap and the stack that our processes never use, we can't actually put anything in there because it's allocated to a process. But if we were to take all of those free spaces and stitch them together, we could probably fit more processes into this whole system. So segmentation then comes around, and the idea here is we're going to logically separate virtual address spaces into fixed size blocks. So base and bounds is segment physical memory into fixed size blocks. Segmentation is, let's separate virtual address spaces into fixed size blocks. And then when we're allocating physical memory for each of those chunks, we're only going to allocate as much as is currently actually used in that segment. So while virtual memory has been segmented into 4 fixed size chunks, we're only using a tiny amount of those fixed size chunks. So we're only going to allocate that much physical memory for each of those different parts. Managing free space with segmentation is a lot harder because we're no longer able to just say, hey, is this block free or not? And if it is free, put the entire address space into it. We have to keep track of which physical, like tiny chunks of memory are actually free or not free. This part here, this is, again, kind of depending on which 2160 assignment you did. The garbage collector is the one I'm specifically thinking about. It is this problem. You are keeping track of which have been allocated and which are not allocated. With segmentation, we have to do the same thing for physical memory. We have to keep track of which parts of it have been allocated and which have not been allocated. If we've got a new process or we're resizing a segment, the issue of where do I put this suddenly becomes a bigger problem because we have to find a space that's big enough for this thing to go. When we're only allocating as much memory as is actually used in a process at that current time, all of the segments that we're putting into physical memory are going to be different sizes. They will be different sizes. So the things that we've allocated are going to be differently sized as well. That leads us to this idea of free space management policies or allocation policies. The segments that we're putting into physical memory are differently sized. So that means that the spaces between segments that we have allocated will also be differently sized, and they may not be big enough, or they might be just perfectly the right size for what we're doing. There are 4 different allocation policies that I want us to take a look at today. There's best fit, worst fit, first fit, and next fit. And I'm going to remind you about what these are. I have given everyone a handout, and it is on my system here called Allocate You Some Memory. This is a little worksheet that we'll work on today. What we've got is physical memory here. This is our physical memory, and we have 16 units of physical memory. The way that each of the allocation policies work is that for each of these different workloads, we're going to be deciding where to put the allocation differently. Each one of these policies is going to tell us how to decide which one goes in which spot. I'm going to verbally tell you what these policies do. It's really small. There's not much that they're doing here. First fit is starting at the top of physical memory, starting at the top of the thing that you're allocating. Scan through it. Do a linear search for a space that's big enough. When you find a space that's big enough, use it. Done. That's first fit. There's nothing more than that. Linear search for something that is big enough. So with workload 2 for first fit, the first allocation is for 1 unit of memory. First fit says, hey, linear search starting at 0. I've found a space that's big enough. None of this is allocated yet, so I will allocate this to be the first one. The second allocation here, allocate 2 units of memory. This one is allocated. This one's allocated, so I'm going to scan the next one. This region is big enough for me to allocate 2 blocks. I will allocate these 2 blocks. Linear search, find the space that's big enough, allocate it. Next fit improves a little bit on the way that first fit works. Next fit does something slightly different. Next fit says, I'm going to keep track of where the last allocation was that I made. I'm still going to do a blind linear search, but I'm not starting at the top of my allocation thing. I'm not starting at the top of physical memory. I'm going to start wherever the last successful allocation was. So with this one, with workload 2, we're going to allocate 1 unit of physical memory here for the first allocation. And then our next pointer will change. Our next pointer is going to say, you've allocated something successfully there. This is the next place that you should start. When you allocate the next 2 blocks here, the next pointer will be updated to the next place that you should start doing allocations. The only difference between first fit and next fit is that we got a pointer that keeps track of where the last one was. Next fit always start at the beginning. First fit always start at the beginning. Next fit start wherever the last place was that you did. Best fit is going to go through something that appears to be a slightly smarter approach to allocating memory. With best fit, we're going to scan through all of the things that are free and try to find the allocation that leaves the least amount of unused space. So I'm going to say at the beginning here that these have all been allocated. These ones have all been allocated, and these are allocated. And we're working on malloc 2 right now. We're working on this allocation. The best fit approach says, let's do a linear search through the unallocated spaces. The unallocated spaces right now are here, here, and here. We cannot put it here because there's only one spot. There's not enough space for us to put it. We have to omit that or exclude that from the place where we can put it. The other 2 places are here and here. We're going to scan through, starting at the beginning, to find a free space. We'll keep track of this one. We'll exclude this one. We'll keep track of this one. And then of the free spaces that we found, we're going to pick the one that leaves the least amount of space afterwards. So for malloc 2, with this specific allocation, we would say that it's going to go here because it leaves only 1 unit free, as opposed to this chunk here would leave 2 units free. So leave the least amount of space afterwards. The worst fit policy does the opposite. I'm going to go through that same approach of I've got some allocations that were made here, and I'm going to do the same malloc 2. I'm going to keep track of the spaces that are big enough, but now I'm going to do the allocation in the one that leaves the most amount of free space afterwards. So if with the best fit, I would choose this one. With the worst fit, I would choose this one because it leaves the most amount of free space. That sounds really counterintuitive. It sounds super counterintuitive. I'll come back to you in a second. It sounds super counterintuitive. The worst fit policy behaves better than best fit because it leaves more big spaces free. So that means as we're going through and finding spots for bigger allocations, like malloc 7 or malloc 5 or malloc 4, the probability of one of those bigger spaces being free still is higher than if we always chose best fit. Yeah.
I was just wondering, I guess, yeah, never mind. I guess it's defined how it is, but like best fit seems like it would find the small space, but then also go at the start of it, and the worst fit seems like it would find the biggest space, but then go in the middle of it.
Worst fit says, neither of these policies actually say where you should put it in the free space. And
Yeah.
typically, and the way that I'm doing it is just put it at the start of that free space. So you're trying to leave as much contiguous free space as possible, as opposed to breaking it into several separate pieces. Yeah, yeah. Yes?
If the memory is empty, they'll cause the best case and worst case.
For the very first allocation, if memory is empty, they're going to do the same thing. They're both going to say, oh, this is big enough, and this is the only free space. In the case of best fit and worst fit, we're going to say, well, this whole thing is one big free space. So we don't have to find any more free spaces because there's just one big free space here. They would just put it at the beginning of the memory. Yeah. Yeah. Okay. So here's what I want to do. I don't want to go through every allocation policy for each of these workloads, and I'm going to change the order of this in that I want this to be, I'm going to call this a 2-based array, and I'm going to make this one workload 5. I want this to be workload 5. I want us to do that one last. What I'm going to ask you to start doing, you know, with the person next to you, with your paper that you've got in front of you by yourself, is for workload 2, I want you to go through the process of applying the best fit policy. When we get to free number 1 and free number 2, what I'm saying is the allocation that was made for number 1 and number 2, we should release those resources. They should be freed. You can do it however you want, but I kind of painfully went through the process of cutting up all these Post-it notes so that you could have something that would stick quickly onto your paper to see which ones have been allocated and which have not been allocated. If you want to do this electronically, this document is up on the course webpage as a PowerPoint document, so you can do it there. So step 1 here that we're working on right now is apply the best fit policy to workload number 2. So please start doing that. I'll give you about 3 minutes to work on it, and then I will come back and I'll show you how this works. Okay, how are we doing? We've got about a minute left. Are you done? Do you want me to start working through it? Okay. Okay. So for workload 2, with the best fit policy, I'm going to take advantage of the fact that I've got this electronic, and I'm going to try to use different colors for this as opposed to just the same color for allocations. So for number 1, I'm going to use, I'll try to pick colors starting here on the opposite side so it's not yellow. I'm going to pick lime. With best fit, we're immediately going to say there's one giant free space. That's the best fit. There are no other free spaces for me to put this in. So I'm going to allocate this one to be number 1. For number 2, we're going to do the same thing, kind of the same thing here. I'm going to pick a bluer color. We're looking at this entire chunk of free space, and this entire chunk of free space right now is the best fit. We're going to leave the least amount of space afterwards, so we're going to allocate that all to number 2. For number 3, I'm going to pick, let's say, purple, and same thing. We're going to just allocate this at the beginning of the free space because it's one giant free space. Everything is going to fit into that one giant free space. Here's where things start to change and get a little bit more interesting. When we free number 1, we're going to release that. So I'm going to release this memory. Number 1 is freed now. And when I malloc number 5, I'll color this one red-ish. When I malloc number 5, there's 2 free spaces that I can choose from. Best fit will say, okay, here's a free space that is big enough for this allocation, and here it is a space that's big enough for this allocation. The one that's at the beginning is the one that leaves the least amount of space around it afterwards. So this is the best choice. This is the best fit for this one. So I'm going to pick that this one is going to be put here. When I free number 2, that releases the resources here. And when I allocate number 7 here, we'll start scanning through this. We'll make this orange. This space is not big enough for 3. This space is big enough for 3. That's the best fit because it's the only fit. So I allocate these 3 chunks to number 7. And the last one that we're going to do here for the best fit policy is number 8. And I'm going to leave that just a black color because I'm kind of running out of colors there in this rainbow. This one is going to do the same process. We've got 2 free chunks here. This one is the best fit because it leaves the least amount of space afterwards. So that one is going to be allocated there. And then we're finished that allocation policy. So best fit here is keeping things close to the top of allocated physical memory. We're almost always stuck with this chunk that's at the end in terms of memory allocations that are all fairly similar in size, and we're releasing and reusing memory that's kind of similar size to what we were doing before. I'm going to come back to you in just a second. I'm going to ask you to think about this. I'm not going to ask you to do it for this policy or for this workload. But with best fit, we're scanning from the top, finding the best spot and putting it in the best spot. How would this change if we were to do next fit instead? What would the layout of these allocations look like if we were doing next fit instead? And we'll do next fit with workload 3, so you get a chance to see it, but just think about it for now. How would it change the way that I've got these allocations done? Yeah.
What if we have a mutable plane that have the same best fit, like the same size?
If you've got 2 that are the same size, you would just pick one arbitrarily then. Yeah, and you'd probably just pick the first one that you found, probably, rather than picking one randomly. Just pick the first one that you found. Okay, any questions about that? It's pretty straightforward, I think. Okay. Let's do workload number 3, but this time I want you to do the next fit policy. So best fit and worst fit, doing best fit in my mind right now is good enough. You'll have the same idea of what to do with the worst fit policy. It's just the opposite case. Let's try do workload number 3 with the next fit policy. So I'll give you 3 minutes. Please go ahead. And we'll work on this together. Whoops, next fit. Does the last allocation move when you call free? No, the next pointer will just stay in the same place that it was before. It will go back up to the top. Yeah, yeah. Okay, okay.
Yeah. Where does the next go? Like, is it 3 way to top or?
So the next pointer won't change when you call free. The next pointer is just going to stay wherever the last successful allocation was. Free doesn't change where the pointer is. And then when you get to the bottom of memory and you're doing the allocation to the next part, you'll move the next pointer back up to the top and start scanning back down again.
I could put 80 off my save.
So 4380 is databases 2. Databases 2 is an operating systems course. Surprise. It's file systems and concurrency because you have to worry about transactions and stuff. Yeah. 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 It goes to the next available spot. Yeah. Yeah. Okay, got 1 minute left on my timer. How are we doing? Doing okay? Now you're under the gun.
Oh, it does. It didn't do anything.
Are you seg faulting here? Okay, let's work on this together. So we're doing next fit. And I'm going to start at the top here. So I'm going to, hey, I didn't know I could do that. All right, awesome. So I'm going to say that my font color here for allocation number 1 is green, and I'm going to do green. Next fit, when the system is in the start state, we're at the beginning. Our next pointer is just at the beginning of the space that we're trying to allocate. We're allocating 7 units here. So 1, 2, 3, 4, 5, 6, 7. And I'm going to set that to be the same green color here. This is where things change about what we had been doing before. We're not just going to blindly start at the beginning. We're going to move this next pointer. So we're going to take this next pointer, and I regret printing the next pointer on the page. I'm sorry. I hope that you took the time to manually move it here. I got a pair of scissors if you really want to cut it out and move it around. The next pointer is going to move to the just after this allocation, wherever the next free space is. When we go to the next allocation, number 2, we don't have to do this linear search from the beginning. We instead can just immediately go to, starting at next, we'll do a linear search and try to find the next available free space that's big enough. For this one, we're going to have, I'll mark it blue here. It's 7 units. The next spot has something that's big enough. So I'll mark this blue. And our next pointer then immediately moves down to the next free space after this allocation has taken place. So down here at the bottom. The last thing that we've got here before we run out of space is number 3. And number 3, we don't have to do that linear search because we're immediately going to see that this remaining free space here is big enough to put that starting at my next pointer now. So I can mark this as allocated. Next here should go after that allocation has taken place. After this allocation has taken place is past the end of memory. So we're doing modular arithmetic, and we're going to move that just up to the top of physical memory here. So there's no space left, but we're moving the next pointer to be after we've placed that memory. What's that? So there's nothing free, but we're still moving our next pointer. And we have to move our next pointer to be after the allocation that we just did. So we're moving our pointer to like the next free spot out of convenience because that is the first place that we're going to find that's free. But in this case, there's nothing left. So we just move it to the next place in physical memory, which happens to be this top. So how do we know that we can't place any more memory? with our operating system, if we were actually writing the code to do this, we would have a linked list that would have like, these are the free locations or these are the allocated locations in memory. And I'm kind of representing that as just they're colored blocks now. So they're not actually going to have a linked list, but in a real implementation, we would have a linked list that says this chunk is allocated starting here and it has this much space allocated to it. Okay, so we moved our next pointer. We're going to free number 2 here. So we're going to release all of this memory. Our next pointer does not change. It doesn't change when we release this memory. So we're still kind of starting at this spot when we're looking for something. We're going to malloc 1. And our next pointer then is going to, starting here, look for the next free spot. The next free spot is at this location. So when I allocate number 5 here, it's going to find this spot. I'll mark this as allocated, and I'll move my next pointer down. And at this point, there is some place that's free for me to start working. If I free number 3, that's this purple color, I'll release these resources. And then malloc 4, and then malloc 1. So I'm not going to finish that, but we're kind of seeing that we're putting stuff here. One of the properties of the next fit policy that you would see with a bigger address space or a bigger physical memory is that it starts to spread the allocations around. Best fit is going to be stuck close to the top. First fit is going to be stuck clumped close to the top. Next fit is going to spread things around for us a little bit more. Okay with that? Okay. Now I'd like you to apply all 4 policies to workload number 5. Don't do it, just do it in your head. Just do it in your head. I changed this, sorry. I changed this. This is workload number 5 here. If you want to do it on paper, please be my guest. Go ahead and do it on paper. But do all 5. Have we visualized it? Let me visualize it for you. There's 2. There's the next 2. There's the next 2. This is true for all policies. There's the next 2. This is getting really tedious already, just like clicking around. They're all the same. They're all identical. They all behave in exactly the same way. They're all identical. Segmentation and free space management policies are a problem that we have to deal with when we've got differently sized chunks of things, differently sized segments, differently sized allocations. Heap allocators use allocation policies. They use free space management policies. We wrote that code that calls malloc a million times or whatever, and it only changed the segment size some small number of times. Heap allocators all use allocation policies. Here is the JE-malloc repository. And in the JE-malloc repository, I like this one a lot because in the changelog, they tell us that they started by using the best fit policy and they switched to using the first fit policy because it gave better performance. The me-malloc allocator here uses, as we go down here a little bit, in this page.c file, which is a kind of a hint to where we're going, It uses next fit as a policy instead of best fit or worst fit. So J.E. Malik is using first fit, me Malik is using next fit. This is the source code. Oh my God. I don't want any of these cookies. But what's off? I don't even like clicking those buttons. And so what I often do is, I mean, my ad blocker is usually like blocking these things on my behalf. But there, goodbye cookies. The malloc that you are using with glibc, this is the source code for glibc. This is the source code for the actual malloc function that you call when you call malloc. Doesn't use any of those policies. It uses a different heuristic entirely based on the size of the allocation request that's being made. You don't need to know which policy each of these things use, but they are using these allocation policies. And they're using these allocation policies because for the code that we're writing, when we call malloc, it's often with different sizes. We're allocating different sizes of chunks of memory. So they have to use these allocation policies. Why don't we discuss this in terms of the Linux kernel, though? Why don't we discuss this in terms of an actual operating system? Heap allocators, not part of the operating system. They're not part of the operating system. They're part of our standard library. We can replace them at runtime if we want to. Some of the stuff that we've done in this course, we've said like, hey, look, here's some source code. Very little of what we've talked about in this course, but at least one thing we've said, hey, look, here's some source code in the Linux kernel. Segmentation fault is when you try to access memory that's outside of the segment that's been allocated to you. The Linux kernel does not use segmentation as a virtual memory policy. Windows doesn't use segmentation as a virtual memory policy. Nobody uses segmentation as a virtual memory policy. Nobody uses this. Nobody actually uses this in practice anymore. This is a really nice page. I'll put a link to this up on the course webpage. This is an article by Ryan Stan, and it describes some of the idea of virtual memory, paging, and segmentation. Segmentation here is a feature of the 8086 microprocessor from 1976. 1976. The Intel x86 architecture is the only architecture that ever used segmentation. Nobody else used it. So like ARM doesn't have segmentation as an option. It doesn't even have it as an option. You can't use segmentation on ARM that I'm aware of. I mean, you could make it happen, I guess, somehow, but the MMU that's on there, I believe, doesn't support segmentation at all. Segmentation fault is a lie. It's a terrible lie. We don't actually use segmentation in the Linux kernel. Segmentation fault, as it is, it's not actually being faulting on segments. It's not faulting on segments, it's faulting on pages. It's faulting on pages. This structure that we've got here, when we have these workloads where we've got all of the allocations being the identical size, all of these policies behave exactly the same way. With file systems, we've got these chunks, blocks, or clusters that are all the same size, and they are either free or not free. We don't think about allocation policies in terms of file systems because it doesn't really make sense to think of allocation policies. There's either a block that's free or there's not a block that's free that we can use. Paging is where we are going to go starting tomorrow. But to give you a quick intro here, when we did base and bounds and allocated full address spaces, we had this problem of internal fragmentation, space that was allocated, but we couldn't actually use it for anything. With segmentation, there's a problem of external fragmentation. We might get into a state with these allocations where there's not enough space in between the allocated chunks that we can actually put a new allocation. Paging takes both of those ideas and tries to put them together. Let's separate our virtual address space into fixed size chunks and our physical memory into fixed size chunks. We're trying to minimize internal fragmentation, so things that are allocated but not usable by other things, and we're trying to eliminate external fragmentation. We'll talk about this tomorrow. Yeah, I'm just going to skip all this stuff. We're already 1 minute past, and I'm grateful that you're giving me that extra time. I hope that you have a great night, and I will see you tomorrow. Bye, everyone.